objective of this part is to calculate the pH of any solution. Suppose you have a solution of acid or acids, the solution of base or bases, or a mixture of acids and bases. To find the pH of the solution, we have to calculate the concentration of HCO+ in the final solution, then applying pH equal minus log HCO+ in solution, and then we find the pH. Another way to find the pH without doing calculation or without proving a formula is to know the nature of the species present in the solution. And according to this species, we have a corresponding formula that can be used directly, but you have to justify the approximations. In the first part, we will calculate the accurate pH of any solution without approximations, and we have steps to be followed. Step 1 is to determine what are the species present in solution. Consider, for example, HCl. The species present are HCO+, and when we say we have HCO+, so we have OH minus, and we have Cl minus. If we have acetic acid in solution, the dissociation of acetic acid is not complete. So in the solution we will have acetic acid remained, we will have acetate formed, HCO+ formed, and OH minus. In step 2, we apply the principle of conservation of species. That means when you start with initial number of mole and 0 of a substance, and this substance in solution is transformed to other species, the number of moles of all forms of the species formed is equal to the initial number of mole of the starting material. In step 3, we apply the principle of electroneutrality based on solution neutral. The equivalent charge of positive is equal to the equivalent charge of the negative, or simply the sum Zi Ci is equal to 0. In step 4, we write the equilibrium constants expressions of all equilibrium present in our solution. So by applying these steps, we will have the accurate pH formula. Don't forget that we can use, therefore, the formula without a proof, but at condition to know the domain of approximation in the solution. We will start the pH calculation of strong acid solution of concentration C. And we have two cases. Case 1, the strong acid is slightly diluted. And the case 2, the strong acid is highly diluted. To find the pH formula, we have to follow the steps. Step 1, what are the species present when HA is put in solution? Since HA is a strong acid, it will dissociate completely to HCO plus and A minus, and we don't have HA remained. So the species from HA are A minus and HCO plus. The presence of HCO plus indicates the presence of OH minus. Step 2, the conservation of species. HA dissociates completely to HCO plus and OH and A minus. HCO plus has two sources in the solution. The HCO plus from HA solution and the HCO plus from the auto-ionization of water. But A minus in the solution has one source, which is the complete dissociation of HA. So if the initial acid has initial concentration C, so A minus formed in the solution equal C. And HCO plus is equal to HCO plus from HA dissociation plus HCO plus from the auto-ionization. So HCO plus in the solution is not exactly equal to C, but A minus is. Step number 3 is to write the electroneutrality principle. The charge, the equivalent charge of negative equal equivalent charge of positive. So 1 times A minus plus 1 times OH minus is equal 1 times HCO plus. Step 4 is to write the equilibrium constant expression of all equilibrium in the solution. We have one equilibrium in the solution, which is the auto-ionization of water, and Kw is equal to HCO plus times OH minus in the solution. So we write the 4 steps corresponding to a slightly diluted solution of strong acid of initial concentration C. Now we have to do the approximations. OH minus in the solution is provided by the auto-ionization of water. We don't have other source of OH minus. And since our solution is not highly diluted, is slightly diluted, so we can neglect OH minus. By other word, we neglect the auto-ionization of water. In this case, we have A minus plus OH minus equal HCO plus, and OH minus is negligible because we neglect the auto-ionization of water. So A minus equal HCO plus equal the initial concentration C0 or C. pH is equal minus log HCO plus in the solution. So pH for a strong acid equal minus log C0 or minus log C. This formula can be used only if the acid is strong and the acid is slightly diluted, or in other words, when we neglect the auto-ionization of water. What is the domain of validity of this formula? We obtain this formula when we suppose that OH minus is negligible with respect to A minus, and a substance is negligible with respect to another substance if the concentration is at least 10 times less. So OH minus is less than A minus divided by 10 implies OH minus, according to the equilibrium constant, is equal Kw divided by HCO plus. So Kw divided by HCO plus is less or equal A minus divided by 10 implies 10 minus 14 divided by the concentration of HCO plus in the solution. I said that HCO plus in the solution has two sources. The dissociation of the strong acid HA, so it gives concentration HCO plus C, and the autoionization that provide HCO plus, but we neglect the autoionization. So HCO plus in the solution is equal to C. Less or equal, A minus is by the conservation of species equal C, so is less than C over 10 implies C square is greater or equal 10 minus 13. So the concentration of the strong acid is greater or equal 3.2 10 minus 7, and the pH of the solution is less than or equal 6.5. What is the meaning of this validity? If you have a strong acid where its concentration is greater or equal 3.2 10 minus 7 mole per liter, you can apply directly the formula pH equal minus log C, and the pH value obtained will be less or equal than 6.5. So in the first part, we prove the formula one time, and we determine the condition of the validity. So now, if we know the condition of validity, if we know the domain of the concentration of the strong acid used, we can use this formula directly without proof. Second case, suppose the acid HA used is strong, of initial concentration C, but is highly diluted. We follow the same steps. The species present are HCO plus and A minus from HA dissociation, and we have OH minus from the autoionization of water, or we say the presence of HCO plus indicates the presence of OH minus. The conservation of species indicates that A minus is equal to C, since A minus has one source, which is the complete dissociation of HA. HCO plus has two sources, HCO plus from the dissociation of HA and HCO plus from the autoionization of water. The electron neutrality principle, A minus plus OH minus concentration equal HCO plus. Step 4, we write the equilibrium constant expression. We have one expression, which is the Kw, the ionic product of water, equal concentration of HCO plus times concentration of OH minus in the solution. Since the HA is highly diluted, the concentration of HCO plus formed and concentration of A minus formed from the HA dissociation are very, very low. So in this case, we cannot neglect the concentration of HCO plus provided by the autoionization of water. By the electroneutrality, we have A minus plus OH minus equal HCO plus. As we said, HCO plus has two sources from HA and from the autoionization of water. OH minus has one source, which is the autoionization of water, and A minus has one source, which is the complete dissociation of HA. Since the acid used is highly diluted, so the concentration C can be neglected, and in this case, A minus is negligible with respect to OH minus. Therefore, OH minus equal HCO plus, and since Kw equal 10 minus 14 at 25 degree, so the concentrations are equal to 10 minus 7 molar. pH is always equal minus log HCO plus in the solution, so the pH equal 7. What is the domain of validity of this formula? In this formula, pH equals 7 is obtained when we suppose A minus is negligible with respect to OH minus. So the concentration of A minus is less or equal OH minus over 10, less than 10 minus 7 over 10. So the concentration of A minus is less than 10 minus 8 molar. And since A minus equals C, so the concentration of the acid is less or equal 10 minus 8 molar. What is the meaning of this domain of validity? Suppose you want to calculate the pH of strong acid. If the concentration of the acid in your exercise is less or equal 10 minus 8 molar, so you apply directly the formula and pH equal 7. Now a new case of concentration of the strong acid. What would be the pH of a solution of strong acid where the concentration is between 10 minus 8 and 3.2 10 minus 7. We follow the same steps: species present, HCO plus, OH minus, A minus, conservation of species, the concentration of A minus equals C, the principle of electroneutrality, A minus plus OH minus concentrations equal concentration HCO plus, and the expression of Kw equal HCO plus times OH minus in solution. In this case, we could not do any approximation. So A minus plus OH minus equal concentration of HCO plus is written by this way. In case 1, we neglect A minus with respect to A minus. In case 2, we neglect A minus with respect to OH minus. In this case, in this domain of concentrations, we could not do any approximation. So HCO plus equal A minus, which is equal to C, plus OH minus according to Kw expression equal 10 minus 14 divided by HCO plus. So we have a second degree equation where HCO plus is square minus CHCO plus minus 10 minus 14 equal 0. To find the concentration of HCO plus and to deduce the pH, we have to solve this quadratic equation, and we have two solutions: one concentration of HCO plus accepted and other possible concentration of HCO plus rejected. So as a conclusion, according to the concentration of the strong acid, we have three domains of validity, or we have three different formulas of the pH. in grade 12 in college, when you want to calculate the concentration of strong acid, you apply one formula, which is pH equal minus log HCO plus equal minus log C equal PC. But now we have three formulas for the strong acid, and it depends on the concentration of the strong acid. So according to the concentration, if it's less than or equal 10 minus 8, so the pH is equal to 7. If the concentration of the strong acid is greater or equal to 3.2 10 minus 7, so the pH equal minus log C, or simply the pH equal PC. And if the concentration is between 10 minus 8 and 3.2 10 minus 7, so we apply the solution of quadratic equation HCO plus square minus CHCO plus minus 10 minus 14 equal 0. So we find the concentration of HCO plus accepted, then we apply pH equal minus log this concentration. We can write this domain of concentration according to minus log C. So if minus log C is less than 6.5, or if C is greater than 3.2 10 minus 7, so the pH equal minus log C. If minus log C is greater than 8, or if the concentration is less or equal 10 minus 8, so the pH of the solution equals 7. And in the domain minus log C between 6.5 and 8, we solve the quadratic equation HCO plus minus CHCO plus minus 10 minus 14 equal 0. By following the same strategies as in the calculation of the pH of strong acid, we will calculate the pH of a strong base of concentration C. And we have three cases. The first, the solution basic supposed NaOH of concentration C is slightly diluted. We write the steps. Step 1, what are the species present? NaOH will give Na plus and OH minus, and the presence of OH minus indicates the presence of HCO plus. The conservation of species, Na plus has one source, which is the decomposition of NaOH, so Na plus is equal to C. OH minus has two sources, OH minus from NaOH and OH minus from the autoionization of water. HCO plus has one source, which is the autoionization of water. The electroneutrality principle, the equivalent of the negative equal to the equivalent charge of the positive. So 1 OH minus concentration equal 1 Na plus 1 HCO plus, and the equilibrium constant expression is Kw. By approximation, we could not neglect Na plus and OH minus in the solution, since the solution basic is slightly diluted. But what we can neglect HCO plus from the autoionization of water, since the solution is basic. So OH minus equal Na plus plus HCO plus. We can neglect HCO plus with respect to Na plus, and therefore we obtain concentration OH minus equal concentration Na plus equal C. When we have base, it's better to calculate the POH. So POH equal minus log OH minus in the solution equal minus log C equal PC. And since we have relation between POH and pH, pH plus POH equal pKw, so pH equal pKw minus POH, so pH equal pKw plus log C. What is the condition of validity for this formula obtained? We obtain this formula by supposing HCO plus is negligible with respect to Na plus. So HCO plus is less 10 times than Na plus divided by 10. So HCO plus is less than C over 10. By the same way as the calculation done in the acid base, we obtain a concentration which is greater or equal 3.2 10 minus 7 molar. So when we have a basic solution, when we have a base, strong base of concentration C, and the concentration is greater or equal 3.2 10 minus 7, so the pOH of the solution equal minus log C, or the pH of the solution equal pKw plus log C. The second case, suppose the base is not highly diluted. The species present HCO plus OH minus Na plus. The concentration of Na plus equals C. The electron neutrality OH minus equal Na plus plus HCO plus, and the equilibrium constant Kw equal HCO plus times OH minus. Since the base used is highly diluted, so in this case, Na plus concentration and OH minus concentration are very, very low, and we could not neglect the concentration of HCO plus from the autoionization of water. So by approximation, the autoionization of water could not be neglected. OH minus equal Na plus plus HCO plus. Na plus and OH minus are very low value. We want to compare now Na plus and HCO plus. Since the solution of NaOH is highly diluted, so the concentration of Na plus is very, very low. It can be neglected with respect to HCO plus in this case. So we obtain OH minus equal HCO plus equal 10 minus 7. So the pOH of the solution equal minus log OH minus equal 7. And the pH plus pOH equal pKw equal 14. So the pH is equal to 7. The condition of validity of this formula obtained is by the same way as the calculation in the strong acid. When the concentration of the base strong is less or equal 10 minus 8, this formula is valid, and pH equal 7 or pOH equal 7. In the third case, suppose the concentration of the strong base is between 10 minus 8 and 3.2 10 minus 7. We write the same steps: species, conservation, electron neutrality, equilibrium, constant expression, but in this case we could not do any approximation. So OH minus equal Na plus plus HCO plus. Na plus could not be neglected with respect to HCO plus, and vice versa. So OH minus equal Kw over HCO plus equal Na plus, which is equal to C, plus HCO plus. So in this case, we obtain a quadratic equation: HCO plus square plus C HCO plus minus 10 minus 14 equal to 0. It's better when you have a base to work on concentration of OH minus POH, and when you have acid, to work on concentration HCO plus and pH. Since we have base, I prefer to use OH minus. So the relation OH minus equal Na plus plus HCO plus, we transform HCO plus as a function of OH minus, and we obtain OH minus equal Na plus, which equal to C, plus HCO plus equal Kw over OH minus, implies OH minus square minus COH minus Kw equal 0. It looks like the formula obtained for the acid, but in this case, in the base, we replace HCO plus by OH minus. So we have the same strategy of work. As a conclusion, according to the concentration of the base, we have three formulas. If minus log C is less or equal 6.5, by other word, if the concentration of the base is greater or equal 3.2 10 minus 7, so we apply the relation pH equal 14 plus log C. If minus log C is greater than 8, by other word, if C is less or equal 10 minus 8, so the pH equal to 7. We can write this domain of validity according to the concentration of OH minus. If minus log C is less than 6.5, we apply the relation POH equal minus log OH minus in the solution equal minus log C equal PC. And if minus log C is greater than 8, so the POH is equal to 7. And if minus log C is between 6.5 and 8, we solve the second degree equation according to OH minus square minus COH minus Kw equal to 0. Comparing the domain of strong base with that of the domain of the strong acid, it's the same, but we replace pH by POH and the concentration of HCO plus by the concentration of OH minus.